Hello everyone. So we continue in the last part of the diffractions and polarizations chapters. Okay. So last time we discussed about what a diffraction is, right? We're starting from the slit, okay, and then you treat the slit starting from more than 2. So we start from 3 and then we see the result from the end slit, okay, and finally we discuss about the interference patterns of the what we call grating. So it's the multiple slit device, okay, and then we start on the discussions. Okay, so we talking about in the situation where the wavelength is comparable to the apertures, okay, and then when you see that if the wavelength start to be larger than the apertures, you're gonna see more wave spread, okay. So so that is the phenomena called the diffractions, and I already mentioned that in our class we're talking about the Fraunhofer diffraction. So we're talking about the pattern that we see far away, so that we can approximate the light rays that travel from the aperture are parallel to each others. Okay. Then we discuss about the single slit diffractions. Okay, so the open slit with A. Okay, and we're talking about the condition for the destructive interference. A sine theta equal to the m lambda, where m starting from 1, okay, plus and minus 1, plus and minus 2, okay, and when theta equal to 0, that is the bright central regions, okay. Then we already we prove on the intensities, okay, and we say that, okay, when we have the system which is slit, for example, the double slit Young double slit experiments, so what we're gonna see, it's basically the combination of the interference pattern and the diffraction patterns, okay. So you multiply the intensity from two phenomena together, and that's what you're gonna see in the experiments, okay. So you will have the envelope from the diffraction patterns, and then in the envelope you see the intensity go up and down from the interference patterns, okay. And then we already count, for example, how many fringe that you can see, for example, in the single in the central maxima, okay. So for today, it's gonna be, I think, quite quick about for the details we're gonna discuss. So the first one is what we call the circular apertures and the resolutions, okay. So why we are interested in the circular apertures? Because the nature it's come with the circular apertures. For example, your cameras, okay, it's a circular apertures. Your eyes is circular apertures, okay. So that's why we are interested in this one, okay. Your eye is not a slit, okay. Your system around you, I mean, like a telescope, it's not a slit, okay. It has a circular apertures, okay. So the behavior of the circular aperture is more or less the same as the single slit, okay. So you're gonna have the central peak maximas, and then it's gonna go down, and it's gonna go up and down like this, so you can see the fringe, okay, in the same way, okay. The difference is that for the circular aperture, you're gonna see in the form of the disc. We call it the iris. Okay, and the difference is that for the dark fringe, the first one, okay, the first minimum. So if you go back to the diffractions, so the first minimum, it's gonna be, is it? Okay, here. So the first minimum, it's gonna be at the theta equal to the lambda over A, right? This is a slit. Okay, so this is the first minimum. So the first minimum, it's gonna be theta equal to the lambda over A. Okay, let's take a short note here. Okay, for the slit. Okay, the first minimum is psi theta equal to m lambda over A. Okay, and then this thing can be approximate to be theta if it's small. Okay, but for the circular apertures, it's roughly the same, but it's different. So the first minima, it's gonna be at theta equal to the 1.22 lambda over A, okay, or over the diameter of the diameters of the apertures. So A in this case is diameters of the apertures. Okay, so it have the factor 1.22 here. Okay, we will not prove it because to prove it's you will need the polar coordinates to work on that, and the knowledge of these special functions. So that's, I think, beyond the level of this course. Okay, but if you're interested to prove that, I think no one stopped you. You can try to do it by yourself. Okay, this kind of proof, it should be circulate around. You can just say circular apertures 1.22 proof or something like that on Google. So it's you should able to find it. Okay, so this is a circular aperture, so it's nothing special than the single slit diffractions, just that you have these factors pop up. And then for the resolution, so for example, in the situation that you have two light sources, okay, if you have two light sources like two stars, and the star and the starlight, it's reaching you, that you have the telescope here. Okay, so what we call the resolution is that how your device can separate between two sources of light. Okay, so we have the criterion called the Rayleigh criterion, is that if you have two sources of light, okay, you can see that this thing can be split or this thing can be resolved, okay, if the maxima of one object is at the minima of another object. Okay, so you have two two diffractions patterns, and then if one of that interference pattern, the maxima, it's in the it's aligned with the minimums of another object, that's we call that the pattern are just resolved. Okay, you start to see two objects, you can identify two objects. Okay, if it's beyond the first minimum, that's clear that you can see. Okay, it can be this way because the intensity of the first minimum and intensity of the first of the central maxima and the next one, it's very vary. I mean, it's it's not it's far from each other. Okay, the value. Yeah, so that's why you can use the central maxima to be as a to identify the resolution of your device. Okay, so you can see that from the figures, if your objects, okay, your object of interest, they are close to each other. Okay, the pattern of the diffraction are very close to each other, so it's closer than the first minima, so that you're gonna see as a single object. Okay, so this is what we call the Rayleigh criterions. So, nothing special, just that the minima of one object is aligned with the maxima of another object, and that's it. Okay, so this is the circular aperture and the resolutions. So next one, it's a small topic called the diffractions of the X-ray by crystals. Okay, so you already know that for the electromagnetic wave, there are vary of the wavelength, right? So you're gonna have starting from a very low frequency, large wavelength, for example, for the radio wave, microwave, the infrareds, and then you start from the visible light, okay, starting from the red zone to the blue zone, okay, and then if you go a higher frequency, you go to the ultraviolet, and then X-ray and the gamma ray, okay. The X-ray is discovered by the Ringen, okay, and the wavelength is roughly it's less than, it's from the figure, it's about 0.1 nanometers. Okay, so it's very small, right? 0.1 nanometers. 0.1 nanometers. So it's going to be very, very small. So the question is that how can you see the the diffraction patterns if you use the X-ray? Okay, because you're gonna have a very small aperture, very small slit, let's say that. Okay, to make the order of the wavelength and the order of the width of the slit are comparable, so that you start to see the diffraction patterns. Okay. So the one applications coming from the Max Theodore Louis. So he used the X-ray, okay, to study the atomic structures of the crystals. Okay, so what exactly has been done is that you start from the shining the X-ray source to the crystals. Okay, and then so when the you light you shine the X-ray source to the crystals. Okay, but when you shine that, you have the what we call the collimators. Okay, to collect just only the ray that have that can pass the hole. Okay, you have the small hole here. It's like the way you select the direction of the ray. Okay, then you select on a very forward directions, it's go to the crystals, and then you put the screen behind that and see the patterns. Okay, so this is called Louis diffraction patterns. Okay, and this one can be used to study the crystals. Okay, so this is for example the patterns of the single crystal, which is the number A, and a pattern for the enzyme Rubisco. Okay, I don't know what it is exactly. You may need to Google that. Okay, and this is how it looks like. And with this kind of pattern, we can reconstruct back what the structure of the crystal should be. And then we have another applications of using the X-ray. Okay, so this is what we call Bragg peak. Okay, so basically the concept is that when you shine the when you give the X-ray source, okay, it radiates and then it's go to the atomic the molecules, the atom of the crystals, and then it's gonna reflect. Okay, and then you have the same wavelength, same phase come in. Okay, and then it start to reflect, and then you can see that you start to have the path difference, right? So where is the path difference? The path difference is here. Okay, so you're starting from the same phase wave. Okay, and then if the path difference create the phase difference, that's you're gonna see from the interference patterns. Okay, so for the constructive interference, in this case, okay, so you need to have the condition of the 2d sine theta equal to the m lambda, where m equal to 1, 2, and 3, and so on. Okay, be careful because the path difference now it's not just d sine theta. Okay, it's 2d sine theta because it's coming from the before the reflections and after the reflections. Okay. Okay. So when the wave go out, okay, it create the interference pattern. It can be destructive. Okay, so this one is destructive. This one is did I put the same figures? Yeah, I think I put the wrong figure. I'm sorry. One need to be constructive. Okay, it should be going out with the same phase. Yeah. To say, yeah, this maybe I just note that this is the wrong figures. Okay, it need to go with the same phase. Okay, so it's create the constructive interference. Okay. Do you think something is strange in these figures? Something that you not do it normally? Okay, if you're looking in the figures closely, you're gonna see that we define something different here. Okay, because normally we define the angle of the incidence. So this is the normal from the plane of incidence, right? Normally we define this angle as the incidence angles. Okay, it's always like this in the optics or in the slits. Okay, in the slit we define the angle in this way. Okay, and this is the angles. Okay, but for these applications, that what we call Bragg, what we define, it's the theta, it's here. Okay, it's measured from the reflecting surface. Theta here is measured from the reflecting surface. Okay, So it's defined differently. So when you use it, okay, just be careful that what the theta means in these formulas. Okay. But if you know that, it's fine. I mean, it's already clear. Okay, you use the equations and then you define the theta properly. Okay. So in this case, you can find the distance between planes of atoms. Okay, plane of the crystals. Okay. Okay. Then we have the last topics. So as you can see that this video should be very quick. So we are talking about the polarization of the light. Okay. The polarization of the light, it's basically the property of the EM wave, electromagnetic radiations, and it tells you the magnitudes, sorry, the direction of the vibrating of the electric field. Okay, so the polarization's direction, it's basically a direction of the vibration of the electric field. Okay. So let's imagine the situation. So you have the E and B, right? And then E cross B is the direction of the propagation. Okay, so this E, it's the direction of the electric field vibration. It's called the polarizations. Okay, and in nature, the light can be unpolarized. Okay, so this angle can be anywhere, right? For example, if you're talking about the light going to you, okay, going out from me to you, so this is the direction of the propagations. E and B can be in this way. Okay, this is E cross B, so you could go out. It can be in this way, it can be this way, it can be this way. So it can be in any orientation. That's fine, because when you have E, you need to control B, and then E cross B give you the direction of the propagation. So it's freely, let's say it have a free choice of what direction it should be. Okay. So that's what we call the unpolarized light. Okay, just wave moving in the same direction where the electric field point in the random orientations. Okay, then if it pass what we call the polarization filters, or any material that have the property of the that have the optical property to create the polarizations, it can be the polarized light. Okay, so there are, let's say, roughly two kinds of the type of the polarizations. So the first one, it's called the plane or the linear polar light. Okay, so in this case, the direction of the vibration is the same for all waves. Okay, if you can see from the figures, you have the unpolarized light passing the polarizing filters. Okay, the polarizing filter will absorb the direction of the polarizations, which is not aligned with the axis. Okay, we can discuss this later. And then it selects just one direction out. Okay, so this is called the polarized light. Okay, it can be a plain linear polarized light. Okay, another kind of depolarization is what we call the circular polarization. So the electric vector, it's rotate about the direction of the propagations. Okay, instead of the selecting just one orientations, it select this one, and then it select this one, this one, this one. It's go circular. Okay, so that's what we call the circular polarization. Okay, so there is a way to create this thing. Okay, the first one is the polarization by selective absorptions. So you have the material that can absorb, okay, the unpolarized light, okay, and then the output from that one, it's become the polarized light, okay. So this is how the system look like, okay. You first have the polarizer, okay. So the polarizer have the axis, transmission axis, okay. The light that pass only the direction of the electric field that are in the same as the transmission axis can pass, okay. So in this case, you're starting from the unpolarized, so the electric field that oscillate in this direction can pass, so you have the polarized light, okay. And then you have the second polarizer, we call it analyzer, okay. Analyzer has the angle transmit axis, okay, with the angle theta with respect to the polarizer, okay. From this case, we can calculate the intensities, okay. So the intensity can calculate from Malus law. So I equal to the I max cosine square theta, and the theta is the angle between transmission axis of the polarizer and the transmission axis of the analyzers, okay. Yep, so this is what we call the polarization by the selective absorptions. So there are two important people that contribute to this thing. First is Malus, as he construct this law, and then Herbert Land, who found the materials that can create the material of the polarizations by the absorptions, okay. Okay, so this is the polarizations by selective absorptions. So the last one is what we call the polarization by the reflections, okay. Instead of you have the material and then the unpolarized part or the polarized light pass, you create the polarized light behind the materials. You can also do it by the reflections, okay. So we cannot prove it. We will not prove it in this class, but we have the conditions that you can use it. Okay, so if you're starting from the Maxwell equations, you can write the boundary conditions. Right, the boundary condition is the condition at this point. Okay, where you have the incidence, the reflected, and the transmit. Okay. And you can say that if you have if the incidence ray incidence, and then it's create the angle, what we call the Brewster angles, okay. The reflected ray will be polarized, okay, and the conditions is that the angle between the reflected ray and the refracted will be perpendicular to each other, okay. The angle is right angle, so 90 degrees, okay. And the condition is that you can find the Brewster angle by this formula. So tan theta I, so this is the Brewster angles, okay. So it's here, it's equal to the n2 over n1. So you find the index of refractions from the second mediums divided by the index of the refraction of the first medium, okay. And then that creates you can find tan thetas, and you can find the theta using the arctan, right? So that angle is called the Brewster angles, okay. So that it can create the reflected ray as the polarized light, okay. Yeah, so I think this is all for this short discussion about the diffractions, patterns, and the polarizations. Okay, actually I should include it in the first lectures, but sorry, I didn't make it in that time. Okay. Okay. So I think this is all for the exam on the April 20th. Okay, it's finished at this point, the polarizations and the diffraction. So you have 3 topics that you should review during the Thai Songkran Day. It's the electromagnetic wave, the interference, and the diffraction and the polarizations. Okay. How the exam will be, how the exam will organize, we will announce it very soon. Okay. But I think the most important is that you finish the videos, and then we're gonna do the live tutorials on next Monday. Okay, I don't know which date it is. 11, right? Yeah, on the 11th. And then we should be ready. You should be ready for the exams. Okay. So for today, there are not heavy calculation, just the concept of the polarizations, the concept of the diffractions, and the concept of from the X-ray. Okay, concept of the circular aperture and the resolutions. Okay, so I think this is all the topics we cover. Okay, this is the list of the topics in survey. So you cover diffraction patterns, narrow slit, resolutions, circular aperture, gratings, diffraction of the X-ray, and then the polarizations. Okay, I think this is all. So the next video will be on the special theory of the relativities. Okay, it's gonna be much fun on the calculations and the problems to solve. Okay, thanks everyone, and see you on the live class on Monday and the next video on the special theory of relativities. Bye bye.